Hello, welcome to another brief video lesson on CCD imaging, planning your image for a non-moving target. This lesson will take you through a thought process when setting up for an observation/imaging run for an object that is not moving through the sky. This will discuss topics that have been covered in previous lessons and therefore will not spend a great amount of detail on those topics here. This lesson should be viewed as a guidance and a process. And to be clear, non-moving object means a galaxy or a star. I know stars have proper motion, but what we're doing is we're differentiating between asteroids and comets and other objects such as stars, galaxies, and so on. Timing, computer clock, if necessary. For some of these projects, exoplanet transits, for example, having an accurate time clock on the computer that's doing the imaging is essential. In some cases, the computer controlling the images system may be automatically calibrated. In some cases, it may not. If it's not, you can use GPS, the United States Naval Observatory, or freeware internet programs such as Dimension 9 that will calibrate your clock against a known standard. Very important when the timing of a transit, such as a photometry project, is key. Ensure the clock is calibrated relative to universal time, local or daylight savings time. You can then calculate this further into Julian date or Basilian time if necessary. Target location and visibility. After you know your target's position, the right ascension declination, you can use any of the following to get that: planetarium or online catalogs. Once you have it, you'll then want to understand when it's visible during the night. Your planetarium software may tell you that, the SkyX, Starry Night Pro, Stellarium, what have you. If you don't have some of those available to you, you can go to a website located here with the URL, and it will help you determine when an object is rising in the sky. Note that you're going to need to know the location of the desired observatory for this calculator to be effective. And what it's going to provide for you, it's going to show you an altitude above the sky starting at 0 all the way to zenith, and it'll show you for your target along a given time period what its visibility is. And so using mean solar time, it'll tell you those particular hours. Now remember, solar time, sidereal time. Sidereal time is relative to the rotation of the stars, but what we know is solar time, from when's the sun at noon to the next day when the sun's back at noon. That is solar time. Also, as the object rises in the sky, you can look to the right and note the air mass as well. So you can see what your air mass is going to be for a given observation. In some cases, like a photometric project, air mass is going to be essential because you don't want light extinction from the atmosphere. In a case like a double star, it may not be as essential. So use the air mass consideration as you need to. Scheduling your imaging run. Understand the goal of your imaging to best determine the integration time, the exposure time, and the filters to use. Pretty pictures will require 3 or 4 different filters, and those are basically luminance as a black and white, the red color, the green, and the blue, and then all of these will be combined. This is known as a process called LRGB. So these 4 filters will combine to make the pretty pictures that you see in astronomy books today. Exoplanets may require at least 2 different filters. Those will be determined by the team requesting the observation. Late K or M star classes may require red or infrared range of filters. Your integration exposure time. Bright stars will require less integration time. However, if your target is a faint star and there are bright stars in the field of view, you may oversaturate those bright stars. For example, let's take a CCD image right here. And let's say that this small star is my target, but I have a very big star right here. Well, I know that with this bright star, I may have to image this faint star, which is my target, up to 120 seconds. Well, I'm most definitely going to saturate this, and I'll see the star, and I'll see blooming spikes coming off of this. That is okay if it's what's necessary to get the target star in our image. However, if our target really is the big star and not the smaller star, we'll have to lower the integration time so that we don't get any blooming and we don't oversaturate that image. You will have to determine the best time based on the magnitude of the object you're measuring. Ensure the integration time for each filter is the same. This allows a similar flux count for each filter without a time bias. So if I'm going to shoot 60 seconds in red, then shoot 60 seconds in blue and IR, etc. Have the time be the same. Set a time that at least provides you a signal to noise ratio of 100 or greater. Are you going to use a cadence? A cadence is a way to shoot images over time. If you are measuring a nova and you want to get a light curve for a nova, your cadence may be once a day, once every 6 hours or so. If you're measuring an eclipsing binary star or an exoplanet transit, you're going to do immediate picture after picture after picture to get a good light curve of that event. If you're imaging a Mira type variable, your cadence could be once a week. How often do you need to do that? So you have to determine what the time frame between when each picture is necessary. Calibration. You have to determine whether or not your imaging system already has a set of calibration files of these. Remember, most calibration files are binned at 1x1. If you bin at 2x2 or 3x3, you will have to have calibration files that are also binned at the same rate. If you don't have these, you'll later need to get them to calibrate each image. Calibration can be conducted during imaging, but not always necessary, as it can be conducted after the imaging run. At the end of the run, you need to look over your images. You have to make sure, see if there are bad images in the frame. For here, we have loss of tracking. In this particular image, these are bright pixels. This is a dark image, what we call a dark frame, because these are ignited pixels that are showing up as stars. They're not really stars. They're just like a pixel that's turned on all the time. You also get these streaks in here, which are hot rows. That's an imperfection in your CCD camera. Or perhaps you didn't take a picture at all. Or you've got what's called dust donuts inside of your image. You've got to find these and you've got to fix them. Dark subtraction, bias subtraction, and flat subtraction can fix all three of these. Nothing can fix a blurry picture or one that's lost tracking. In sum, the lessons provided you a rough overview of how to plan for an imaging session for an object that's stationary, not a comet, not a meteor, stationary object. Within this lesson, there were assumptions of basic CCD imaging knowledge. For more information on those fields, or if you have forgotten something, please go back and consult the video lessons for those appropriate topics. One advantage to imaging non-moving objects is that if the run is unsuccessful on a given night, for whatever the reason, you can rerun the plan on another night, on the next night for that. This is not the case for a moving object. Thank you for your time, and we look forward to seeing you in future brief video lessons.